Welcome to Module 3 in our series on constrained optimization. The last module dealt with the Karush-Kuhn-Tucker conditions, the KKT conditions. We use those to solve constrained optimization problems with both equality and inequality type constraints, whereas in Module number 1, we only solve problems with equality type constraints. Now this module builds upon the second one, and what we're going to do is look at some alternative ways to incorporate inequality constraints into problems that we had previously understood how to solve. More specifically, we're going to look at a way to transform or convert certain types of inequality constraints into equality type, and then we can just apply those or use those within methods that we learned in module number 1. There are other ways to integrate inequality constraints into the equality constraint optimization problems we looked at in module number 1, aside from applying KKT specifically how we presented it in the last module. One alternative method involves the introduction of an additional variable called z. So if we assume that h of x is less than or equal to 0, which has been pretty much the case throughout all of these modules, this variable is defined as z is equal to negative h of x. We know that all feasible values are greater than 0 because of this. So if we say that z feasible is equal to minus 1 times h of some feasible x, and we know that h of any feasible x will be less than or equal to 0. That's by definition, right? The feasible state has to satisfy this inequality. So we invert the sign or reverse the sign, and we end up with a value of zf that must be greater than or equal to 0. And again, the f subscript just refers to it being a feasible state. So this method, as compared to KKT, allows us to replace the inequality constraint h of x is less than or equal to 0 with an equality type constraint that reads h of x plus z is equal to 0. And the upside of this method is then we can, from this point forward, use many of the methods that we've already learned. So it yields an equality-only constrained optimization problem, although one with one inequality that does remain, that's z must be greater than or equal to 0. However, this does not prevent us from applying methods like the method of Lagrange multipliers, although we're going to use MATLAB in this specific module. The inequality constraint applied directly, and inequality constraint applied directly to a decision-like variable, which z is one of those, is easier to manage than h of x is less than or equal to 0. And we'll see that's the case when we look at the use of the linear programming function in MATLAB. All right, so let's take a look at the transform in symbolic or mathematical terms. So our original form of the problem is shown to the left. We want to minimize an objective function x. It's subject to some equality constraints g of x, as well as some inequality constraints h of x is less than or equal to 0. And we have for this module, we're assuming that x must be greater than or equal to 0, and actually I'm going to mark this piece out because we don't have any z yet on the left-hand side. All right, so this is our original problem. Objective function, equality constraint, inequality constraint, and another inequality constraint, but that's applied only to the decision variable. So then we can apply our inequality to equality transform, and the first line doesn't change. We're still trying to minimize f of x. However, now, instead of being subject to a g and an h, a set of equality and inequality constraints, our inequality constraints are gone. And we're left with a set of equality constraints that is larger, and that is composed of both the g of x and the h of x put together. However, we can't forget that we need to add this z value in order to convert it from inequality to equality. Now, why plus or minus? Okay, essentially this comes down to the way that h of x is defined. We are assuming that h of x is less than or equal to 0, and that's the way it's defined. And for that case, we use a plus. It's positive. It would be negative if we were to use the opposite, but we're really not dealing with that case in this module. And then we have two inequality constraints that are applied to decision variables. We still have x must be greater than or equal to 0, and now we add an additional one which says that z must be greater than or equal to 0. There's actually a way around this by using z squared instead of z. However, the downside of that is it makes some of the equations nonlinear, so there's pros and cons there. But the upside is that once we have applied this transform, we have an equality-only constrained problem that we can solve in many of the ways that we presented in module number 1, and we treat z the way we would treat any other decision variable like x. All right, so let's take a look at an example, and then we're going to jump over to MATLAB and look at how to solve it. So we want to minimize an objective function that's composed, and these all take on a linear form. So we have CF1 times x1 plus CF2 times x2, which is similar to saying CF transpose times x. It's subject to an equality constraint AG1 times x1, AG2 times x2 minus BG. H of x is equal to AH1 x1, AH2 x2 minus BH. Now, these are all just scalar values. AG1, AH1, AG2, AH2. And again, we're carrying over that requirement we had from the previous slide, which doesn't always have to be utilized, but in this case we're going to keep it. We're going to assume that our x values need to be greater than 0. All the decision variables need to be greater than 0. Okay, then we apply our inequality to equality transform. Really nothing happens to our objective function. That stays the same. Well, I guess something does happen. We can add the 0th term at the end, right? Because what we're really doing is adding z as a decision variable. And if we're doing that, that means that this c of f needs to get a little bit longer. So you end up with cf transpose 0 times x and z. And so that's essentially what's reflected right here. We still have cf1 times x1, cf2 times x2, plus 0 times z. Our equality constraint, the original one, stays the same. I don't think I need to repeat this. We have a similar 0 times z term. And then we have here where we converted our inequality to an equality, AH1 x1, AH2 x2, minus BH, and here's where our z comes in, right? We have to keep track of that z. We have to include that z right there. And this expression in green is essentially just h of x plus z equals 0. This is the same expression we showed before. Now, instead of having a single inequality constraint on the decision variable, we have two. X needs to be greater than or equal to 0, as well as z, the new variable we added, needs to be greater than or equal to 0. So here's the MATLAB code that we used to solve. Let me throw the QR code up on the screen if you want to take a look at it. I'll also have the link in the description if you want to download it that way, but I encourage you to check it out. So let's jump over to MATLAB and take a look at how we can solve this constrained optimization problem with both inequality and equality type constraints. All right, so now we have the MATLAB script up in front of us. I'm going to go through it line by line. Some of it will be pretty similar to the examples we looked at in the previous module, but a couple of the steps are different. For example, we're going to use a different function, MATLAB function, or to solve, because both of these, well, this example is purely linear. So I start off by clearing the memory, clearing the screen, pretty much standard what I always do. Then we begin by defining the system constants. Now I'm going to do this randomly, and I just repeated here the objective function, which is CF1 times x1 plus CF2 times x2. The equality constraint, again, same thing, AG1 times x1 plus AG2 times x2 equals BG, or you could say minus BG equals 0. The inequality constraint, AH1 times x1, AH2 times x2 is less than or equal to BH, or again, you could shift that to the other side. And then this example has a decision variable constraint that x both x values need to be greater than or equal to 0. So all these functions employ a linear form, which is going to affect how we're going to solve. Okay, so I started off by solving the problem considering only the equality constraints. And so we're ignoring the inequality constraints for this portion. Now, here's where we get to the function that we're going to use. Instead of solving, we're going to use linprog. So this is a MATLAB function that allows us to solve linear programming problems or linear constraint optimization problems. And you can look at the MATLAB documentation if you want to see how it works, but there's just a couple of inputs, and I can go through them really quickly. So the first, this would be the coefficients of the objective function, hence that's why we put array CF right there. This and this, right, this would be where you would put mat AH and array BH. So essentially this is the matrix that serves as the coefficients of the x values for the inequality constraint, and this is the offset values for the inequality constraint. And so you can see we did something similar here except for the equality constraints. So since we defined our equality constraint in terms of AG times X, right, is equal to BG, I'm just placing those values into the linear programming inputs. And so that's why I put mat AG right here and array BG. And as you can see, right, this would only work if you have this very specific form. It has to be a linear form, or else you won't be able to use this. You won't be able to use this function specifically. Then we have 0, 0. So what is this? We're telling MATLAB that the minimum value of x for both is 0. And then these are the max values. And so I just put them at infinite because we don't have a set maximum value. Now, in order to run this as neglecting the inequality constraints, what we have to do is essentially put these empty brackets in here for the inequality constraints. And then this will spit out the solution. Okay, so that is kind of just introducing us to how the linear programming functionality works. Now, what we can do is solve the inequality constraint problem using both. Again, using linear programming. So this statement right here is exactly the same as the one above, except now you can see that I included mat AH and array BH. So those are both present. So this would take into account both the equality and the inequality constraints. I didn't change the limits over here. Okay, so then, now this is probably the more interesting part relevant to what we did in this module. So now I want to supply this problem to the linear programming function, but in terms of equality constraints only. So we're going to use that z value in order to convert the inequality constraint to an equality constraint. Now what this requires me to do is to redefine all of our functions in terms of 3 decision variables, right? Because z essentially becomes a decision variable. And so, like I showed in the PowerPoint, right, our objective function becomes cf1 times x1, cf2 times x2 plus 0 times z. And so now you can see that I took those values, cf1, cf2, and I transferred it to this new array over here and with the 0 for z. Okay, next, what we need to do is redefine our equality constraints. And so this is similar to what I called the new equality constraints, new G. And so what I'm going to do is I'm going to take what previously was previously what we had was 2 single row oriented matrices or arrays, AG and AH. And so now I'm going to combine those together into a matrix. And so what we'll end up with is the equality constraints will have 2 rows. One will contain the original equality constraint, and the second row will contain the inequality constraint. Now, right again, we need to define both of these in terms of x1, x2, and z. So for the equality constraint, which is up here on the first row, I just include the original values, and then a 0 as the coefficient for z, right? Because we don't really use z in the statement of g. And if I go into the PowerPoint, you can see it right here. So this is the reason why there's that third 0 when we're defining AG. Okay. So then we have mat AH1, mat AH2, and the number 1. And so that's similar to what we have right here. So we have AH1 times X1, AH2 times X2, okay, and then a coefficient of 1 for Z. And so this number 1 right here, this is the place where we include Z in the calculation. So what we've done now is we've created a new matrix, which I called AG3. Perhaps, I don't want to rename it here on the fly, but let's see here, mat AG3. Maybe it's better to rename that as mat AG new. All right, so I'll replace that. Maybe that's easier to understand. And so this contains the combination of both AG and AH from before. And then I do the same thing over here for the BG and the BH values, so the offsets for both of those. And I'm going to go ahead and also rename that. One second. All right. And so we have BG new, and that contains both those values. So previously we had a single row AG and a single row BG, and now we have a 2-row AG and a 2-row BG. So, right, if you look back here, you can see what we did was took the blue and the green statements and we combined them together into a single row. So now we can apply the linprog or linear programming MATLAB function as before. We just have to input our new values. So we have our new set of coefficients for the objective function. I changed the name of this one as well. We don't have any inequality constraints, right? Because we got rid of those. We converted those to equality constraints and we included them in here in the mat AG new and array BG new. We set the minimum for all 3 of our decision variables, x1, x2, and z to 0, because all 3 of those need to be greater than 0. And then the maximum for all 3 of those is infinite. And yeah, that should be where we get our answers. So we can take a look here. This just compares the solutions. So what we expect to see when we run this is really 3 solutions. Array x opt3, the third version of the optimal value that's generated by this function. Let's see, array x opt1, which is generated here, and there should be one in the middle that I missed. Array x opt2. So it essentially goes in order. The first one was generated by the MATLAB function that only considers equality constraints. The second one considers both inequality and equality constraints separately. And then the third one is the result of us converting the inequality constraint to an equality constraint. So what we expect to see now, if I run this, is 3 identical solutions. So hopefully that's the case. So let's scroll up. So we end up with 0.673, yep, 0.673, yep, and then down here 0 and 0.673. Down here is the z value, which we don't have any practical use for. So the good news is that this code does demonstrate how we can take a constraint optimization problem, albeit one that's defined in a linear form, and solve it in 3 different ways. I mean, the first one is really kind of deficient because we ignored the inequality constraints, but it shows how we can use linear programming, use that function to consider the inequality constraints as inequality constraints, or put them into an equality constraint form. So back to our PowerPoints, a couple of clarifications I wanted to make here before we end this module. So I think I said this before, but this module predominantly assumes that we're dealing with minimization, right? You can formulate these problems in terms of maximization, but to keep things simpler, we're just dealing with minimization, at least for now, just dealing with minimization type problems. And we're also assuming that h of x is less than or equal to 0, right? We could very well define these constraints as h of x is greater than or equal to 0, but again, I don't want to go through all these different permutations and make this topic even more difficult to understand. So we can reverse any of these, minimization and maximization, less than, equal to 0, greater than, equal to 0. As long as we're consistent, then we change the other parts that need to be changed. We talked about several different signs, and I wanted to come back to that. So under these assumptions above, this one and this one, the Lagrange function always employs a plus for the inequality term. I know that we had plus or minus, but when we're dealing with minimization or these assumptions up above, it's always plus. And then when we were talking about the inequality to equality conversion, we introduced this variable z, and this was plus or minus. But again, if we're assuming that h of x, sorry, not this one, if we're assuming h of x is less than or equal to 0, then it will be plus z, and we need for mu to be greater than 0. So again, we can reverse the signs as long as we keep everything consistent. Now, one thing that I didn't put on the slide here, and I almost wasn't going to say, but it's presented in many textbooks, and maybe you haven't picked it up yet, is we can go in the other direction, right? We can take an equality constraint and convert it to two inequality constraints. So essentially what you end up with is g of x is less than or equal to 0, and g of x is greater than or equal to 0, which if you're not dealing with greater than, you could say negative gx is less than or equal to 0. So if you have an equality constraint, g of x is equal to 0, you can produce two inequality constraints which are equivalent. Essentially, g of x is less than or equal to 0, and minus gx is less than or equal to 0, which, not to be repetitive, is the same as g of x is greater than or equal to 0. And then obviously, right, you have less than or equal to 0, but they're pointing in two opposite directions, so the only value that would satisfy both would be the one where it's equal to 0. A couple example notes. Also, I forgot to state when we defined the example that it was required that x be equal to 0. This is not something inherent to the problem. It was just part of the example as I formulated it initially, but I forgot to put it on that first slide. Also, I said something that was a bit confusing. We didn't necessarily expect to see the same solution for all three of the cases in the MATLAB, really only the second and the third, right? Because we had three cases. We had the first where we ignored the inequalities, right? Then the second was considered both equality and inequality. And then the third was considered both, but what we did was we incorporated the inequality into the equality. So we really only expected these two to match, not this one. The reason why all three matched was because the inequality constraint was ultimately non-binding, and so it didn't have an effect on the solution. So we ended up with the same solution for all three of those cases. But you cannot ignore the inequality constraint always and expect to get the same solution. Then I think the last thing here is talking about the linear programming function in MATLAB. I wanted to make a slide that was specifically on that, but I think the idea came across when we looked at the MATLAB. This is a function that's specifically designed to address linear optimization problems with a form similar to that of our example. And that's the reason why we put in the CF, the AG, the BG, the AH, and the BH algebraic objects in separately or as a single unit, because linprog, or the linear programming function, already understands how to process those. Also, we talked about signs of penalty terms quite a bit, and I wanted to clarify that. So, for minimization, any added negative term is good, right? Because it moves the value, the output of the objective function, towards that minimum optimal output. As such, any violation, h of x, if it's greater than 0, right, because that constitutes a violation, it should be positive in order to remain quote-unquote bad, right? Negative is good, it reduces the output value, and positive would be bad. So this is why the multiplier mu must be greater than 0 to ensure that the sign of this penalty does not flip. And again, making sure that the penalty violation remains a negative thing. Again, where bad translates to moving our output away from the minimum optimal value. And so that marks the end of this module on the conversion between inequality and equality constraints. Next, we're going to be diving into module number 4, which is an introduction to duality, and then several modules after that are going to be tasked with discussing, explaining, analyzing the concept of duality and how we can apply it to constraint optimization problems.